We have started writing a lot of behavioral code in Verilog, and as you may recall, behavioral modeling describes the behavior of a circuit. You write code to describe that behavior of a circuit, and then you hope that it will infer the circuit that you originally designed and that you have in mind. So in this video, I'll give you some coding guidelines to help you write a little bit more robust code that is a little bit or more or less buggy. So this code in here, or some of these guidelines, is stylistic, but some are not. So the very first one is actually not necessarily stylistic, and it tells me use blocking assignment whenever you're actually using or writing code for combinational circuit. We have seen this recommendation mentioned when we talked about blocking and non-blocking assignment, but I feel it's important to have it emphasized in here. So whenever you're writing code, think, am I writing a combinational circuit or a sequential circuit? If you're writing a combinational circuit, you have to use blocking assignment. Just as a reminding, a blocking assignment lives within an always statement and has this equal sign. And a non-blocking assignment, which is a deferred assignment, is usually used for registers. So if you're writing sequential circuits, register, flip-flop, think non-blocking assignments and only use this type of assignment. And if you actually follow these two guidelines, it will save you a lot of headache and a lot of errors in your code. The third guideline that I have in here is assign a variable only in a single always block. So let me explain this with an example. So in here, I started a module, and this module takes a couple of inputs A and B and gives me a single output. And what I want to do is I want to open this always statement, and then this is actually the sensitivity list is A and B. We're going to say begin and an end. And here what I decided to do is like X equals A or B or and B. You can do whatever you want here. Okay. Verilog allows me to write several always statements. I don't have to stick to one of them. I can write another one. For example, I can just say here always at A comma B, and then we say begin and an end here. And this always statement can be inserted before the first one that we wrote. Remember, just like order doesn't matter when we're talking about a whole always block, not internally into it, okay? All right, so inside this always statement, what I want to do is I want to say, okay, well, X equals A or B. So the third guideline in here, it's telling me assign a variable only in a single always statement. So I'm actually violating that guideline in here. And I'm violating it on purpose to show you what's happening. So this always statement gets invoked or gets started if A or B started. And what it is telling me is X will be equal to A and B. But at the same time, this always statement in here is actually telling me it's A and B. If they change, you're going to tell me that X is A or B. So what I did is I assigned X in a couple of places to the output of completely different circuits. And this is what we call a race condition. This will create a race condition because we do not know which one will be evaluated first. Remember, Verilog is a concurrent language, so this gets evaluated and this gets evaluated at the same time concurrently. So it might evaluate this first or it might evaluate this one first. So the circuit that will infer is actually unknown. It could be either one of them. We do not know. And you might take it between different EDAs. For example, like if you take a Vivado or you take it to the version in Intel, the one that Altera, which is Quartus, I believe, you might get some completely different results. So let me show you what we'll get here. So when I drawing the schematics, I got that X is actually connected to the output of the OR and it's connected to the output of the AND. And this is in digital logic, it's illegal because I might get a conflict. What if this is a 1 and this is a 0? For example, if A is 1 and B is 0, the output of the OR would be a 1, but the output of the AND will be 0. So I'll have a 1 and a 0 connected together and you'll get an illegal operation. So the third guideline is a must. Whenever you're actually using multiple always statement, just make sure that you're only assigning a variable in only one of them. Do not assign it, whether it's blocking, unblocking, I don't care. As long as you're assigning to that variable, assign it on only one of them so that you don't get that race condition. The last coding guidelines, it actually is not a must as per se. It's mostly stylistic more than anything, but I have found it very useful when I'm dealing with sequential circuit. It actually helped me organize my thoughts and helped me avoid a lot of errors. So what this guideline tells me is you should separate the memory components, which are registers, into individual code segments. Specifically, is the following. what it's telling me is follow this diagram. This diagram shows me the general synchronous system. Like any general synchronous system will be composed of some components like a subcomponents of these. But generally you'll have some sort of storage elements in here. A register, a couple of flip-flops, whatever it is. This is where we actually store everything. This is where we connect the clock to. And you usually decide whatever will happen to it next time or the next clock cycle by some sort of a logic. Generally speaking, it's a combination of circuits at the very input of that. So this is why we call it next state logic, and this is why sometimes it's called state next in here as the output. So this next state logic, generally speaking, is connected to some external signals, and it could be also connected to the actual output or the current state or the current value of the queue. So you take these two inputs in here and you generate whatever is the next. And lastly, sometimes you take the output directly from the registers, but sometimes you do some sort of logic on it. So you have some output logic. So you might have like a couple of signals coming. You take the AND of them, the OR of them, whatever you want to do. And generally speaking, the output logic is also a combination circuit. Sometimes not only do you take the output in here, but you also take the input signals into the output logic to generate an output in here. And we'll get to that later when we talk about finite state machines. These are the differences between Mealy and Moore machines. But anyway, for now, what's important is that guideline is telling me the following. I'm just going to reread it again. It tells me separate memory component into individual code segment. What it really is telling me is if you're writing something, you're describing a synchronous system, a sequential circuit, just make sure that the registers are written in their own always statement. The output logic is written in its own combination circuit statement, and this one here is written in its own. You do not have to follow this particular one. It's a style. You're going to see that this style will generate verbose code, but that code is really robust and it's really easy to follow and it's easy to debug. So let me give you an example of how to write such a code. So in here, I'm giving an example of this particular circuit, okay, or this particular system. So in this system, I decided that, okay, there's, instead of a register, I'm giving you a couple of flip-flops, which are a register. A register is just a bunch of flip-flops. Okay, so this particular here is these two in here together. So I'm just giving the different segments and I'm coloring them differently. So the output logic in here, which is this guy in here, it just happened to be F. And if you care about G, we can output it. For now, we're going to output G. This is the output logic. There's actually no circuit, just the wires coming out. But we could have, like, this is actually this one here as well. There's no output logic. It's just the wires. All right. And the last segment is actually this one in here. And this is actually the next state logic. And this is, generally speaking, a combinational circuit. And that is composed of these particular circuits in here. That's the combinational circuit we have. All right, so let's get started. We'll go to Vivado and write code to describe this particular circuit in here so that I show you how you can separate the different components separately. So I've started a new module. I called it Coding Guidelines, and I'm following this particular diagram. I have three inputs, A, B, and C, and of course I should have a clock because it's a sequential circuit. And I have a couple of outputs, F and G. I mean, the circuit here tells me G can or cannot be. Like, I'm just going to output it. You can just ignore G if you don't want to, but I'm just going to output it. So the third guideline is telling me you have to separate the input, the next state logic, the register logic, and the output logic. So let me explain to you how I usually do this. So what I usually do, I do the following. I say like, okay, how many registers do I have or flip-flops? In this particular case, I have a couple of flip-flops. So I say, okay, let me define the following. I'm going to define F reg and F next. And these will be the following. I'm going to write these signals on the diagram itself. So this one here, I will say this is the current value of F of the register that is actually, I just called that register F. So this is what I called F and this is what I'm going to call G. And the next value would be, the input will be F next in here. So what I'm trying to do is I'm trying to distinguish between the current value and the next value of this register. So I usually do that. The same goes with the G. So I'm just going to write it in here. So we have G reg. Okay, and usually G next. This is just a style and a convention that I use, and I found it to be very helpful. Okay, so I'm going to do this one here. I'm going to say G next and G registers. Just for the sake of consistency, we're just going to write them in the same order, but you don't have to. All right, so we have done this. So what this tells me is the following. You have to separate your input logic, your register logic, and your output logic separately. So let's start with the register logic, whatever you see in green in here, highlighted in green. So it's as simple as saying, okay, well, these are just a couple of flip-flops or registers. So I will do this and I will make sure that they're activated with the positive edge of the clock. Okay, and I'm going to say begin and an end. All right, so now what I have is I have a couple of registers in here. And because I'm dealing with registers, that means it's sequential circuit. So any assignment I should do within this always statement should be non-blocking assignment. All right, so what should I do in here? Well, what I should do is I should tell it what should be the F register value in the next clock cycle. So all I have to do is say, okay, the value for the register that is called F, it could be a register or flip-flop. In this case, it's a flip-flop. It could be multiple bits, and at that point, it'll be register. Okay, the value of this flip-flop, the next value should be, again, continuous non-blocking assignment, not a continuous assignment. Non-blocking assignment should be the next value that I wish to do. And I'll figure out what the next value in a completely different always statement. I can do the same exact thing with the G, okay, and this is G next. Okay, so what I'm saying here again is I want the next value of the next value of F to be assigned to that register at the next clock cycle. And that's basically, I just separated that logic. I don't have to worry about anything else. I'm just saying this is how I want you to be updated. Next, I can just say, okay, let's say the next state logic. Okay, the next state logic, and this is usually a combination circuit. You feel free, you can use it with an always statement or maybe continuous assignment. It's up to you if you want to use data flow modeling. It's just a combination circuit. This is whatever is described in pink. I'll just use another always statement just to show you. And this other always statement, we're going to have a sensitivity list, and we'll figure out the sensitivity list in a minute. Okay, but what do I want it to do? Well, I wanted to describe these two things in here, and these are basically this and that. So let's describe the one that is actually at the output of the F. So what this is telling me is the following. Well, F next, this is the next value of F. This is actually why I wrote this F in here. That's basically what's connected to this particular register. I don't care about the register at this point. Okay, what do I want this to be? Well, I want it to be A and something knotted. What is that? It's actually this particular signal, which is the current value of G. And that's where that G reg will become useful at this point. Like if I just use G, I might get confused. Is it the current value or the next value? What I really want is the current value or the G reg. So I'm going to just say G reg. Okay. And that's pretty much it. We don't have anything, we don't need to worry about anything else. So let's see, why isn't it liking it? Well, it's not liking it because the sensitivity list, I didn't figure out what the sensitivity list is. We'll figure it out in a second. Okay, the next one I'm going to do is, let's take a look at the G in here. So this G is actually connected to this guy, and this guy is just the OR of B and C. So I'm saying is G, the next value of G should be just B or C. And I'm technically done. I can really, I mean, one way to figure out the sensitivity list is just to put the star, and Vivado and Verilog will figure it out for me. However, just to be consistent, and I usually like to write them, I know I usually look at the assignments and I say, well, if G-reg changed, A changed, B changed, or C changed, one of the ones on the right-hand side changed, I want that always statement to get executed. Okay, and that's basically it. That describes the next state logic. So I separated that. So what's left for me is the output logic in here. So if for some reason or another we decided that we want the output to be the F and the G, I just take these and put them in an AND or an OR whatever I want. But at this particular point, I don't actually have any actual logic. It's just wiring. So all I have to do is just rename that F register to F and the G register to G, because these are the outputs that I have in here. So all I have to do is just put them in a continuous assignment, and that's what I will do right now. So we're going to do this here, and we can say output logic, and we can say assign F equals F reg, the current value of F, and assign G equals the G of reg. So that coding style that we just described actually tells me that we have to do this. Like that coding guideline is telling me separate your code into registers, into next state logic, and that's a combination of part. And as you might have seen, it's doing that for me in just a minute. Because I wrote it as a combination circuit, this is a blocking assignment, this is non-blocking assignment, because this part is describing registers, and which is a sequential circuit. And here I just decided to use continuous assignment. So I'm taking a look at the schematics. So if I actually zoom a little bit out and then I show you, hopefully you get to see, yes, that's actually the knotted, and this is like, yep, that's exactly what we described. It's exactly what we wanted. All right, so this is how I usually write my code. However, I just want to mention the following. I have separated non-blocking assignment and blocking assignment in completely different always statement, but it doesn't have to be the same. You can actually mix and match them. However, at this point, because you're a beginner in Verilog, you might get confused, and it might give you a lot of errors if you actually combine the two. So generally speaking, I recommend that you stick without them. But just for the sake of completion, I will actually show you just a more concise way of writing the same exact code in here. So this code is very verbose, but it's very easy to follow and easy to track and debug. I'm just going to show you much shorter version. So let me show you. So we can do the following. Instead of doing all of this, I can just say always at positive edge of the clock, okay, begin and then end. And now what I can say is I want f to be equal to a and not of g, okay, and I want g to be equal to b or c. And if you actually run the code, you're going to see that you're going to get the same exact thing like the same exact circuit, and you can run it. That is because we're using a non-blocking assignment. And if you think about it like this here, it's telling me, okay, evaluate what's on the right hand side. What's on the right hand side is a and actually the current value of g, okay, and then we'll assign it at the very end. The same goes with the g. I'll actually assign it the value b or c at the very end, but here I'm using the original value or the current value of g. Anyway, this particular code is much shorter, but you will be a lot more prone to errors because you're going to think this g is completely different than this g. This is the current value of g, this will be the next value of g, and using this name, unless you really understand the differences between blocking and non-blocking assignment, you're going to generate a lot of errors. Okay. So just to give you more styles, so this is the very extreme in here. So I will just show you a different style which actually allows you to combine blocking and non-blocking assignments. We're going to start with the following. I'll just focus on the F for now. We don't need the G, just the F. Okay. Well, actually, we do need the G. So we're going to keep it. Okay, that's fine. So what I'm going to do is I'm going to say the following. All right. Let's do this. I will say AG equals A and not G. And what I will do is I'll say F should be equal to AG. I'm using non-blocking assignment altogether. Of course, I have to define the AG as a register in here. So what this is doing, it's actually just taking a look, and I'm just computing the F next value is actually, I just called it AG. Okay, just because it's A and G, and it's like it involves A and not G. Okay, and what I did is I did the following. I said, okay, you're evaluating this, and then later you're gonna insert the value of AG, and F will take the original value of AG. Okay, we'll see what type of circuit will be inferred with this thing here. B or C. Okay, and then G equals B, C. Let me just make sure that we use non-blocking assignment all the way. All right, so let's do this here, and this is BC. And what I did in here again is I used non-blocking assignment, non-blocking assignment, non-blocking assignment, non-blocking assignment. I just said B or C. I'm just going to save them in a signal. I'm just going to call it BC, and then I'm going to assign it later. So now, if I'm actually to run this code and it's just say, let's see the schematics coming out of this code, I'll get a really interesting error. Taking a look at this, technically it shouldn't have had any problem like with the code that we just wrote, I mean, or differences from the code that we just wrote. But if you take a look at the schematic, I actually have a drastic difference, and that drastic difference are these registers in here. Okay, so originally I only needed 2 registers, okay, and what I did is I got a couple of these registers, or 2 extra. So let's see why we did get this. So we got that because the following, you see this AG in here? It will take the value of A and not G at the very end. So I'll have to actually create some sort of a register to store that value. And F will take the current value of AG, not the one we just uploaded, but the one we actually originally needed. So I have a couple of values of AG, and that's why we need to store it. The one that I'm assigning to F or G, or here, sorry, F, this is the AG, the one that is coming from this guy in here. Okay, and the one that is actually coming before it. So I have to store that one in an intermediary one. Okay, so even though I'm here describing, well, what I'm trying to say in here is you described a combination circuit with a non-blocking assignment, a combination circuit with a non-blocking assignment. It created that extra latch or extra register that we do not need. So the solution for this is a good understanding of blocking and non-blocking, and you actually have to do this the following way. So we're going to do this as a blocking assignment. So what I'm doing is I'm saying AG, you should block everything else till I actually evaluate you. Once I get evaluated, I'll be assigned to the F. And this way I'll get rid of these registers. If I reload this, you're going to see that we'll get rid of this register. So in this particular style, I just use blocking and non-blocking assignment within the same always statement. However, as you might see, it tend to get confusing and it tend to get errors sometimes. So now because I used non-blocking assignment and blocking assignments together, what I have in here is I have generated the circuit that I really wanted. Just to add on, just to make sure that you actually understand what's happening in here is the following. If I actually change the order of the statements, I'll get to the same particular error with the extra register that we have. So if I do this one here, let me just show you. We're gonna make the non-blocking coming first, and then here is the non-blocking coming first in here. There you go. Okay, so we can do this here. This is a G. Okay, and you'll see that we will get the same exact error. It's going to generate the same exact extra register, and the reason why is this F here now depends on the current value of AG or the previous value of AG. It's still like the one that we entered with. Let me just show you that we got that extra one. Yes, we did get an extra one, as you might see in here. So let me explain it very quickly. So what happens in here is F will get evaluated the value of AG that we entered the always at, not the one that we're going to update later. And this AG gets updated. Well, that means I need a previous value and a new value. So I need some sort of a register to store it. Okay. So to sum up, what I really want you to understand is the following. Follow these coding guidelines and it'll help you significantly. The last one is a stylistic. The one here is stylistic. It will generate verbose code, but it will generate code that you understand and it's easy for you to debug.